Boltzmann brain concept, a thought experiment in physics, considers the chance that a single brain might spontaneously create itself in a void. This formation would include all the memories of a life in our universe, an event deemed more probable in this theory than the actual occurrence of the universe. According to current cosmic theories, the Boltzmann brain concept thus acts as an absurd conclusion to examine competing scientific theories. Whereas the brain in a vat experiments deal with perception and cognition, Boltzmann brains are used in cosmology to scrutinize our understandings of the universe's development and principles of thermodynamics. Over an ample duration, random fluctuation could cause particles to haphazardly generate any complex structure, even a functioning human brain. Originally, this proposition only encompassed a single brain with fabricated memories, but physicist Sean Carroll extended this scenario to include the formation of bodies and galaxies as well. The Boltzmann brain concept is inspired by physicist Ludwig Boltzmann, 1844-1906, who in 1896 introduced a theory addressing the universe's controlled chaos, contradicting the predictions of a nascent thermodynamics field. He proposed several explanations, one stating our universe fluctuates towards a state of greater organization or low entropy, contrary to the expectation of a dispersed and homogeneous thermal equilibrium. Ernst Zermelo, a mathematician, developed a theory in 1896 that the second law of thermodynamics was absolute instead of being statistical. To oppose Zermelo's view, Boltzmann introduced two theories. The first, widely accepted today, suggests our universe started from a low entropy state for some unexplained reason. The second theory, published in 1896 but credited in 1895 to Boltzmann's assistant Ignaz Schütz, introduced the Boltzmann universe concept. In more recent times, the Boltzmann brain concept received significant attention as some researchers in 2002 started voicing concerns about human brains being more likely to appear from random fluctuations. This led to the speculation that humans may be Boltzmann brains by statistical standards, possibly mistaken about their past memories. Boltzmann's argument is currently entangled with the unresolved issue of measure calculation in multiverse theories in cosmology. Renowned physicist Richard Feynman suggested a complementary theory in his influential work Feynman Lectures on Physics. By 2004, the scientific community had built upon Eddington's theories, resulting in the theory of Boltzmann brains, the most common observers in a never-ending continuum of thermal fluctuations. This concept implies that eventually, in the universe's final heat death, every conceivable structure, including every possible mind, will be created through random fluctuation over time, the rate of which is subject to the Poincare recurrence time. Scientists Anthony Aguirre, C. M. Carroll, and Matthew C. Johnson challenge that a Boltzmann brain, body, or world doesn't need to suddenly appear, but could instead emerge sequentially through smaller fluctuations, similar to a reverse process of a brain's decomposition. Generally, Boltzmann's thought experiments focus on complex structures such as human brains, which are assumed to be self-aware observers. However, smaller structures that simply meet the criteria for existence are significantly and exponentially more prevalent than larger ones. The time needed to form a Boltzmann brain far surpasses the age of our universe. In the realm of contemporary physics, Boltzmann brains can be formed either through quantum shift or thermal fluctuation, usually involving nucleation. In one guess, a Boltzmann brain would emerge from a quantum fluctuation after an interval of approximately 10-50 years. Notably, a quantum Boltzmann brain would appear from nothingness, endure long enough to have a singular coherent thought or observation, and then vanish into the same nothingness whence it came. It is an entirely isolated entity, incapable of energy radiation. Data indicates that the universe's vacuum is not a Minkowski space, but is likely a de Sitter space with a positive cosmological constant. Hence, in a de Sitter vacuum, a Boltzmann brain could form by the nucleation of non-virtual particles that gradually accumulate from Hawking radiation. The estimated average time for this process is about 10 TeV-70, 6 years. A Boltzmann brain, after completing its activity, would cool down to absolute zero and finally decay as any solitary object would in space's vacuum. Theoretically, a Boltzmann brain could, though with an infinitesimal probability, form at any point during the matter-dominated early universe. Some theorists hold the belief that brains created via quantum fluctuation and potentially through nucleation in the de Sitter vacuum are not considered observers. It is simpler to dismiss quantum fluctuations due to criteria like the lack of interaction with the environment. Carroll theorizes that a deeper comprehension of the quantum mechanics measurement problem would prove that certain vacuum states, incapable of dynamical evolution, cannot foster nucleated brains or any other type of observer. Some cosmologists maintain that enhancing our understanding of the quantum vacuum's freedom degrees within holographic string theory holds the solution to the Boltzmann brain problem. Though confident in his human status, Brian Greene highlights the challenge we face in aligning our theories with the reality that we are not Boltzmann brains. Within a lone de Sitter universe that possesses a cosmological constant, the occurrences of normal observers are finite, limited by the universe's heat death. Assuming the universe's infinite lifespan, the creation of nucleated Boltzmann brains would also be infinite, a notion that unsettles cosmologists like Alan Guth as it would deem us infinitely unlikely to be normal brain. There are exceptions, such as the local decay of a false universe into a Minkowski or a Big Crunch, bound anti-de Sitter space which would prevent infinite Boltzmann nucleation. A lack of a cosmological constant and a dissipating quintessence could also avoid infinite Boltzmann nucleation. One possible solution to the Boltzmann brain problem involves varying approaches to cosmology's measure problem. Our understanding of the normal observer to Boltzmann brain ratio depends on how we interpret infinite limits. The measurement problem also encounters issues with balancing regular observers and anomalously early ones. In instances such as the proper time measure, the typical observer could be a Boltzmann baby, formed through a rare fluctuation in an extremely hot early universe, notably within the infinite multiverse theories. Having even a minor fraction of Boltzmann brains dominate the measurement of the multiverse. As previously underscored, the majority of Boltzmann brains typically undergo abnormal experiences. Renowned physicist Feynman highlighted that a self-aware Boltzmann brain would not anticipate normal future observations. To put it differently, in a universe ruled by Boltzmann, even though most of these minds experience abnormal occurrences, the majority of observers possessing only normal experiences are indeed Boltzmann brains. This is due to the sheer enormity of the Boltzmann brain population in a universe where they are dominant.